Hello everyone, welcome to my channel. I think we got a new circuit here. Let's see the circuit. We have here an LED resistor. This one is a push button and a resistor LED. This one is a capacitor LED and a resistor. So we have three circuits here. And let us see what is this all about. We're trying to build a capacitor circuit here. So this one is our new circuit. This is a previous circuit. So let us see the circuit of each one. The circuit of this is LED circuit. A 12 volt switch resistor LED to the ground. Circuit diagram. We're using the resistor here to protect the LED. So we're using 3 coops and the ohms law here, and we get 500 ohms here, and then this is the layout since this is a previous circuit. Now the second one is a resistor buffer gate. Push the button, LED lights on. So the difference of the circuit here in this is I just connected the push button here and adjust the two components to the side. So this one, we are here making it a resistor buffer gate. I have also a previous video of this circuit. It's the same, current flows here upon closing the switch and stops here because this push button becomes open. And according to the truth table of the buffer gate, no input, no output here. So we get here when you push the button, current flows and making a closed circuit here, computing the resistor here to protect the LED. We got the Kirchhoff's voltage loop, some Ohm's law, and then the symbol, PROBABLE gate, the truth table, and the layout. Since this is my previous project here, let us try to focus on the third circuit. And this is our new circuit here. So the difference of this new circuit, named Capacitor Circuit-Series, is in our previous circuit we have push button here. Now instead of push button, I'm using the capacitor here to see what's going on when you're using a capacitor in series with the resistor. So let us see the current flow upon closing the switch. Current flows here to the capacitor and it's charging, and then to the resistor and to the LED. So it's charging, and then we're using 1000 microfarad capacitor, 16 volts, and it's charging, making the LED turns on. And then using the Kirchhoff's voltage loop here, finding the value of RD here to protect the LED. I have a new technique here, I call it sign technique. When capacitor is still charging, current flows here, then you see the sign here, negative, positive. It's still charging. This is like a sorting here. And positive, negative, anode, cathode. So when the current flows here, negative BS voltage supply passing to the capacitor, still charging, passes here, positive into negative, voltage drop at the resistor, voltage drop at the LED here, positive, negative. So we got this equation. Negative Vs plus voltage drop resistor plus voltage drop diode is equal to 0. According to Kirchhoff's voltage loop, the sum of all voltages in a closed loop is equal to 0. We get now voltage drop across the resistor 10 volts. Using Ohm's law, we get this 500 ohms. The 0.02 here and the 2 volts I'm using in the diode LED is given in the datasheet of an LED. This one. So we computed a value of the resistor here. Now let's see the charging. This is the, we call it time constant, the amount of time when the capacitor is charging, and it is with the symbol tau, which is equal to resistor times capacitor. Should be resistor in ohms, capacitor should be in farad, tau it should be in second. Now time constant here is we have now resistor value 500 ohms, then 1000 microfarad, equivalent to 1 times 10 to negative 6. This converted to 10 cube, negative 6 plus 3 becomes negative 3, and then the equivalent this is 0.001, transposing it to the left. Then we got a time constant of 0.5. To make the capacitor fully charged to its 99.3%, we need a 5 time constant, or 5 RC, or 5 tau, which is 5 times 0.5 seconds. We get 2.5 seconds here. So this is the table for the time constant of the capacitor. One time constant is charging it to 63.3%. 3 time constant, 4 time constant, and in 5 time constant, 5 RC is 99.3% fully charged. And we got the remaining 0.7% here. This is not 100% fully charged 5 time constant, just 99.3%, 5 RC. In 0.7 RC, we get 50% charge. So 5 times constant here is 2.5 seconds. It is fully charged by just 2.5 seconds here. So we got here the given values. Then we have the parts here, capacitor, resistor, LED. And once it is fully charged, what happens? The LED turns off. There's no light here. There's no current flowing here, making the circuit open, broken here. So let us see if that's true. First, that is the switch. This one is the switch. Close the switch. There's a light, and then it's fully charged, and the LED is turned off because it's charging very fast, 2.5 seconds. When it's fully charged, there's no current flow here, LED turns off. So let us see if this is fully charged. Close the switch, close the circuit, or turn off the switch, discharge this capacitor. See, there is a light spark. Now let us begin. Close the switch, and now here, close the switch of the circuit. It's charging again, and it's very fast. That is the equivalent time constant of the charging level of the capacitor, making the LED turns up upon this discharging, charging of capacitor here. So when it's charging, fully charged, there's no current flowing here, making this LED to turn off. So that is the effect of our capacitor in series with the LED. If you put a capacitor here, the same, it is in series, we got the same result if you place the capacitor here in the anode side of the LED. So that is our capacitor circuit. From this mother circuit, LED circuit, we inserted a push button, making it a resistor buffer gate. Now instead of push button, we have now this capacitor. This is the capacitor circuit from our mother circuit LED, and then to the resistor, buffer gate. Now we get this capacitor circuit. That is the characteristics of the capacitor in circuit. Capacitor circuit. Okay. Thank you for watching the video. Bye bye.